All right, we have looked at the derivative of an exponential function as a concept, and we looked at the inverse of an exponential function in order to get us the natural log function if we have the derivative of y equals e to the power of x. So we're just going to jot a couple of notes here as introduction, and then we'll get into an example or two. Notes. The derivative of an exponential function, the derivative of an exponential function is also an exponential function. All right, nothing new there. We know that. What does that mean? It means that if y equals b to the power of x, then dy by dx, the derivative of that function, is a stretch or compression of that same function. Okay? We have discovered this, but we haven't written it this way. So if we are given any exponential function, b to the power of x, the derivative of that function will be b to the power of x, that same function, times k, which can be positive, negative, between 0 and 1, or greater than 1. So it can be a stretch or compression of the original function. So this is where k is some constant. So up until now, we don't know how to figure out that constant. We do know that constant in one specific case, okay? Because we do know that if we're dealing with y equals e to the power of x, if our base is e, the derivative of e to the power of x is just itself. So in other words, when b equals e, comma, k, our constant, is 1. That's going to help us to identify something important, because maybe I'll just write what it helps us instead of proving what it helps us to identify. It proves true for this one, and we're just going to use the property. It's called the derivative of the exponential function. The derivative of an exponential function y equals b to the power of x is dy by dx equals the natural log of b times b to the power of x. So again, what you see here is if you're taking the derivative of an exponential function with base b, you just have that function, but you have a stretch compression of that function, and the stretch compression is a constant that's defined by the natural log of the base. The natural log of the base. Now, that explains why that when you take the derivative of y equals e to the power of x, that you just get itself. Because what is the natural log of the base in this case? Well, the natural log of the base would be the natural log of e, which would be saying the log of e base e, which is 1, right? The natural log of e is 1. So now we can take the derivative of any exponential function, and we know its stretch compression factor. It's just going to be the natural log of the base. So we start off pretty simply, straightforward, and then you can be sure you're going to end up having to combine this with other differentiation rules in other types of functions. But for now, let's go into example 1. Example 1, we are just differentiating exponential functions, and then it's asking us to graph the function and its derivative. We'll just sketch it because we kind of already know what it is. The first one, we are going to take the derivative of y equals 2 to the power of x. Well, according to our derivative of an exponential function rule, dy by dx is going to be this function times a constant, which is defined by the natural log of the base, which is 2 in this case. And then this is as an exact value. Okay, if you needed an approximate value, you would take the natural log of 2, which is 0.693 times 2 to the power of x. And then what we could do is, using graphing technology, we could graph it really accurately. But we have a pretty good idea of what these graphs should look like. So I'll first graph y equals 2 to the power of x. And again, our graphs aren't going to be perfect. It's just a sketch to kind of show us what's happening. This one goes through 0, 1. And it goes through 1, 2. Then it would go through 2, 4. And that's about all that we're going to add, just to give us a reference. So what happens if we take that function and we perform a stretch compression by a factor of 0.693? It's going to be a vertical compression. So our new curve is going to fall just under the original curve. Every point along it is going to be cut down a little bit lower, closer to the x-axis. And for example, it goes through the point, and we're not going to do a whole bunch of points, but it goes through the point 0, 0.693. And that's really good enough. We just wanted to show that the derivative of this is lower, the graph is lower than the original graph. Now, trivia question, when will this change? When will the derivative of y equals something to the power of x, some base to the power of x, when will the derivative graph grow faster than the original graph?
I don't think it ever will. Well, like if the constant's smaller, or if it's less than 1.
So that's what we're asking. When will this constant be less than 1?
Oh, if the base is greater than e.
So as soon as the base is greater than e, we'll have a stretch instead of a compression.
Okay.
And if the base is e, we'll get the exact same graph, which is what we already knew. Okay, we'll try a second one. That is the second one, actually. Y equals e to the power of x. So if we take our derivative, dy by dx, we end up with the natural log of e times e to the power of x. We know the natural log of e is just 1. So we just end up with our same original function, showing us algebraically that the derivative of y equals e to the power of x is y equals e to the power of x. And we could draw that one, but it's pretty boring. The graph just lands on itself. So here's our original function. We could say it goes through 0, 1, because anything raised to the power of 0 is 1. Then it goes through 1e, because e raised to the power of 1 is just e. And our derivative function is going to be right on top of it with a stretch compression of 1. Doesn't do anything. All right, you knew it was coming. Example 2, equation of a tangent. So we have an exponential curve. Y equals 2 times e to the power of x. So we have y equals e to the power of x with a stretch of 2. And we want to find the equation of the tangent at x equals the natural log of 3. So to write the equation of the tangent line, we need the slope at this point and the coordinates of one point on the curve. We can get that a couple different ways. But let's first get that second point. So the critical point, we're going to get using an x value of natural log of 3. So all we need to do, let's make a note here. I'll change colors. Find tangent point. Sorry, not the critical point, the tangent point. Find the tangent point. In order to do that, we're just going to take y equals 2 times e, and we're going to raise it to the power of x, which is now the natural log of 3. Well, again, this one, we know a rule for doing this. We don't even need our calculator anymore. We know that e raised to the natural log of 3, which is just e to the log of 3 base e, is going to be 3. So this is 2 times 3, which is 6, which gives us a tangent point of natural log of 3, 6. We'll save that for later. Now we want the slope. Find slope of tangent. To do that, we take the derivative of our original function. So we apply the constant multiple rule, which says that if you are taking the derivative of a function that has a constant multiplier, you can just take this. You can take 2 times, and you don't need to write all these steps. We're just putting the constant multiplier in front of the derivative of the function, and because the derivative of e to the power of x is e to the power of x, we end up with 2 times e to the power of x, which tells you something fairly interesting, that even if you multiplied e to the power of x by a stretch or compression factor, you're still going to end up with the same function as your derivative. At any rate, to find the slope, now we need to take our derivative function and we need to sub in a value of x, natural log of 3. So we're taking our y prime, and that's going to be our slope at this point, and we're going to sub in natural log of 3 for x. So we've got 2 times e to the power of our natural log of 3. And again, we're in the same situation, in case you haven't figured it out. E to the power of the log of 3 base e is just 3. So we're looking at 2 times 3, which is 6. So the slope at this point is also 6. To find equation of our tangent, we're going to take our point slope form. Y minus y1 equals m times x minus x1. And we're going to sub in the values that we know. We know a y value of 6 corresponding to, I'm going to replace that slope, corresponding to an x value of the natural log of 3. And we have a slope of 6. And now we're just performing some algebra on this. I'm going to end up adding 6 to both sides and distributing the 6 here. 6x minus 6 times the natural log of 3 plus the 6 coming from the other side. And typically we would rearrange this in order to... So again, we're not going to simplify. We're going to use an exact value here. So your y-intercept is, and it's easier if I write this the other way around, plus 6 minus 6 times the natural log of 3. So keep your plain old number first, and it's positive, so that's helpful. But this right here, then, whatever that value is our y-intercept. And this right here is our slope. Example 3, insect infestation. We have a biologist. She is studying the increase in the population of a particular insect in a provincial park. The population triples every 3 weeks. Triples every 3 weeks. So we don't have a doubling period. We have a tripling period. We're going to assume that the population continues to increase at this rate, and initially there are 100 insects. So initial population, 100 insects. Our first question is to determine the number of insects present after 4 weeks. Number of insects, or population, after 4 weeks. So we can see that it's going to triple every 3 weeks. And we're looking for after 4 weeks, so it's going to more than triple. It's going to triple and a bit. So let's find it out. First, we're going to put this into an equation, our given information. So the first thing we need to do is develop an equation, the number of insects based on time, with respect to time. You could use population with respect to time, whatever you want. So we have the number of insects with respect to time. It's measured in weeks. Our initial value is 100. We have a tripling time, so our growth factor is 3. And it's to the power of t, where t is weeks, where t is the number of weeks. Okay, so then to find out the number of insects present after 4 weeks, we really just need to sub in t equals 4. So the number after 4 weeks is the number of insects, n with respect to 4. We just sub that in. 3 to the power of 4 we can do in our head. That's 81. 81 times 100 is 81 with 2 zeros. So we get 8,100 insects after 4 weeks. B says, how fast is the number of insects increasing? How fast is the number of insects increasing? And when you hear something like how fast, your rate of change alarms should be going off, which means we need to differentiate our number function. We need to differentiate n with respect to t, which we said equals 100 times 3 to the power of t. So n prime with respect to t. We have our constant multiple rule. So we're just going to take our 100 out front and leave it there. And then we're going to take the derivative of 3 to the power of t, which is k times 3 to the power of t, where k is the natural log of 3. Okay, so we're getting used to this piece right here. The derivative of 3 to the power of t is the natural log of 3 times the function itself. It's a stretch compression of the function itself. In this case, it's a stretch because our value here is greater than e. It's greater than 2.72. All right, now to find how fast the insects are increasing initially, we want to evaluate, we skipped that part of the question. So initially, again, because this is a exponential function, I just give us something to look at here. The rate of change is also increasing, okay? how can we know that? Well, the rate of change is the slope. The slope of this is increasing over time, so the rate of change is increasing. And the derivative of an exponential function is another exponential function. So the rate of change of that will be increasing, will be increasing, will be increasing, will be increasing. Every derivative will have a similar characteristic in that it will always be increasing. Okay? Which means that if we're going to find the rate of change at the beginning of this situation is going to be different than the rate of change later on. It's going to be different than the rate of change later on. Okay? We can do that by just thinking through the tangent lines at each of these points. The rate of change is increasing. So you can't get the rate of change of the whole situation for always, but you can get it at specific points. So we're going to get it initially at the beginning, and then we're going to get it at our 4-week point that we've already talked about a little bit. So the rate of change initially, right at the beginning of this study, is when time is 0, when no weeks have passed. So we just sub that in to our equation. 100 times the natural log of 3 to the power of 3 times 3 to the power of 0. 3 to the power of 0 is 1. The natural log of 3 is 1.1. And then, anyways, if you just chuck that whole thing in your calculator, you'll probably be okay. You'll end up with approximately 110. So that is the rate of change at the beginning. So that means that if we're going to interpret this, so the number of insects is increasing. The number of insects is increasing at a rate of 110 per week. Okay, and that rate is going to increase. And this is just the very beginning of the first week. Okay, this is the rate at the very beginning of the first week. So this is even going to change from day to day. This rate will change. It will increase. We're going to find out what that rate is at the end of 4 weeks. It's going to be pretty significantly different. So we are, how fast is the number of insects increasing at the end of 4 weeks? At the end of 4 weeks. So after 4 weeks, all we need to do is take our derivative function, sub in 4. That gives us 100 times the natural log of 3 times 3 to the power of 4, which gives us 81 times 100, which is 8100, times the natural log of 3, which gives us approximately 8,899. So at the end of 4 weeks, comma, the number of insects is increasing at a rate of approximately 8,899 per week. So, exponential derivatives. Derivatives of an exponential function. The derivative will also be exponential. It will be a, where can I point? It will be a compression or stretch compression, vertical of the original function. And you can use it in problems of population or investment and other such things that have growth and decay. Practice problems come from page 274. You should be able to do numbers 1 through 16.